Welcome to the Problems Channel Season 2, Episode 37, the episode which I titled East or West, Divide and Conquer, because starting with this episode, we will begin a dedicated study of the so-called divide and conquer problem-solving approach. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problema Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E37, we're asked to cut a single 8x3 piece of wood into two pieces of wood, which when combined can cover a single 12x2 hole perfectly, and the actual challenge in this problem is to generate a solution of the problem using precisely the divide and conquer problem solving approach. Before we deep dive into the underlying mathematics, here is a description of how the divide and conquer problem solving approach works. The description of the divide and conquer problem solving approach consists of three parts, or of, intuitively speaking, three words of wisdom: divide, solve, combine. That is, if we want to solve this or that technical problem using the divide and conquer problem solving approach, then as a first step we should try to divide the monolithic whole into a number of smaller and simpler or primitive parts. Once that is done, we should try to execute the second step, or we should try to find the solutions of all the primitive parts into which we managed to partition the monolithic whole in the previous step. And as the third and the final step of the divide and conquer problem solving approach, and that is quite often the most difficult part in applying that approach to the process of searching for a solution of a technical problem, we should try to find a way to combine all the solutions of all the primitive parts into a solution of the whole at hand. Now that we understand the description of the divide and conquer problem solving approach, let us see how it may be applied in practice. Even though the mathematical problem S2E37 is of kindergarten variety, I urge the mathematically inclined thinkers in our audience not to discard this problem right away, because as far as I am aware, at least 2 units of grown-up mathematical knowledge came out of the scissor cutting problems, which exactly what we have in the mathematical problem S2E39. The first such unit of grown-up mathematical knowledge is called the Wallace-Bolyai-Gerwien Theorem, and the second unit of grown-up knowledge that came out of the scissor cutting problems is the so-called Hilbert's third problem. The Wallace-Bolyai-Gerwien theorem deals with two-dimensional shapes that, in the most interesting case, trap a non-trivial amount of area with nothing but a finite number of line segments that are chained or linked edge to edge, as shown, for example, over here. That shape known as a polygon, and a general term for two-dimensional shapes is lamina, but in most general case, lamina does not have to be delineated by line segments. A lamina shape can be delineated by curved lines, for example, but again, in the Wallace-Bolyai-Gerwien theorem, the only material that we're dealing with is precisely polygons. The close cousins of polygons in 3 space are the so-called polyhedrons or polyhedra, which again, in the interesting case, are 3-dimensional shapes that trap a non-trivial amount of volume inside of them, which is delineated by nothing but the planes or the very polygons that we dealt with in the first case of the Wallace-Bolyai-Gerwien theorem. And it turns out that the question that the Wallace-Bolyai-Gerwien theorem answers is the following. Let's say we take two polygons, and the question that we pose is the following: is it possible to cut one of these polygons with scissors in such a way into a finite number of smaller polygons in such a way that these smaller polygons can be rearranged into the second polygon and possibly conversely. Now, in the main notion that the Wallace-Bolyai-Gerwien theorem operates on is called the notion of equi-decomposability. Two polygons, for example, as shown here and here, are called equi-decomposable if any one of these polygons can be scissor cut into a finite number of smaller polygons, and these smaller polygons can be rearranged into the body polygon and conversely. Here I showed you one example of two equi-decomposable polygons. On the left hand side you can see a polygon that, let's say, loosely is based on the follows arrow that we use in mathematics a lot, and the second such polygon is basically a square. And the reason why these two polygons are equi-decomposable is because, for example, the arrow or the right arrow polygon can be cut into a finite number of small polygons, in this case three triangles: the red triangle, the green triangle, and the blue triangle. And these three triangles can be reshuffled into a shape shown on your right hand side and form a square. And conversely, we can take the square that's shown on your right hand side, cut it into three triangles as shown, reshuffle these triangles in such a way so as to form the right arrow shape. And this is precisely the statement of the Wallace-Bolyai-Gerwien theorem, according to which any two polygons are equi-decomposable if and only if they have exactly the same area. In plain English, it means that if we take any two polygons whatsoever, and if these two polygons have exactly the same area, then any one of these two polygons can be scissor cut into a finite number of smaller polygons, which can then be rearranged into the body polygon and conversely. Now, the answer to the Hilbert's third problem is unfortunately no. If the answer to the two-space problem, let's say, is a yes, any two polygons with the same area are equi-decomposable, it is not the case that any two polyhedrons that have the same volume are equi-decomposable. And the work, if you want to investigate this on your own, dig deeper into the Wallace-Bolyai-Gerwien theorem, then you can actually do it. It's not that complicated because the groundwork for this result was set by none other than Euclid. On your right-hand side over here, I show three interesting propositions that you can look at. These propositions are not very difficult. It's nothing beyond proverbial middle school mathematical curriculum. In Book 1, Proposition 42, Euclid shows how to take any triangle and construct a parallelogram that has the same area as the given triangle. And not only that, in this proposition, Euclid gives us 1 degree of freedom. In other words, in Book 1, Proposition 42, Euclid allows us to specify the magnitude of the interior angle of the target parallelogram. In Book 1, Proposition 45, Euclid does the same, but not to a triangle, but to an arbitrary, as he refers to, rectilinear figure, which in modern speak is basically a polygon. So in Book 1, Proposition 45, he shows how to decompose any polygon into a parallelogram with an arbitrary magnitude, whose magnitude of the interior angle is arbitrary and controlled by us. Lastly, in Book 2, Proposition 14, in Book 2, Euclid develops the so-called geometric algebra. In book 2, proposition 14, Euclid shows how to take any, again, rectilinear figure or a polygon and flip it into a square that has exactly the same area. You see? And now once you know about this, once you know about book 2, proposition 14, in general, the guts or the heart and the soul of the Wallace-Bolyai-Gerwien theorem becomes transparent or intuitively clear, because if we can take any two polygons and reduce them to two squares where the squares have the same area, then boom, voila, there you go. Any two arbitrary polygons that have the same area can be transformed into one and the same square that has the same area, and thus such two polygons become equi-decomposable. There is another notion. If you start digging deeper into the Wallace-Bolyai-Gerwien theorem, you will meet another notion, equi-completability, which means that if we take, for example, any two polygons, then if we add a finite number of other polygons, then we come up with two shapes that become equi-decomposable. But for our discussion, we do not really need it. And when it comes to the Hilbert's third problem, it is important to understand the meaning of the universal quantifier for any. For any, it means that if we take any two polyhedrons that have the same volume, we should be able to come up with an algorithm following which we can cut one of such polyhedrons into a finite number of smaller polyhedrons and then reshuffle the smaller polyhedrons into the second polyhedron. Apparently this is not the case, and it was proved by one of the Hilbert students, Max Den, D-E-H-N, if I'm not mistaken, and he constructed his proof by coming up with the counterexample where he took a cube and a regular tetrahedron of the same volume, and then he showed that it is basically impossible to scissor cut a cube of the same volume and then reshuffle the cut pieces into a regular tetrahedron. But that does not mean that sometimes it is not possible to go through this exercise. That means that sometimes it is possible. For example, in season 1, when we solved a number of beautiful problems which dealt with circumnavigation of popular regular polyhedrons, for example, remember when our curious ant traveled over the outer surface of a regular tetrahedron, it turned out, and we proved, that if the ant travels precisely through the middles of the faces of a regular tetrahedron, then such a circumnavigating orbit or path will actually partition the parent regular tetrahedron into two polyhedrons, which, when, for example, reassembled like so, will construct or put together a polyhedron that has exactly the same volume, but obviously a distinct polyhedron that is different from the regular tetrahedron. And the question over here, if you remember, could be framed as a puzzle. What is this, and how can this be morphed into a different shape? The answer is we simply rotate these two guys one with respect to the other, and voila, we have a regular tetrahedron that has exactly the same shape as the polyhedron that's put together from two halves like. So, and obviously there is way more grown-up mathematics that goes along with polyhedrons in general and regular polyhedrons in particular. For example, here in season 1 we discussed briefly the such regular polyhedrons as a regular dodecahedrons, and over here regular icosahedrons. And for example, some of our viewers may remember that an icosahedron has a group of rotational symmetries that is isomorphic to the finite alternating group A5. If we consider all the axes of symmetry that regular icosahedron has, these rotations, certain rotations, will take it back into coincidence with itself. These are called congruence rotations. And if to these congruence rotations we add the so-called congruence reflections, then we will get a group that is the isomorphic to the direct product of the finite alternating group A5 and the finite cyclic group C2. So as we can see, there is a fair amount of grown-up mathematics that follows from all of this and revolves around this. But how does this relate to our problem? We will answer that question in the next segment. Coming back to our mathematical problem S2M39, what we're given is a physical, or apparently a physical piece of wood. And if we take a physical saw, again, let me show you guys one of my saws that I have. Here we go. If we take a physical saw and we begin cutting a physical chunk of wood with a physical saw, then every blade of every saw has non-zero thickness, which means that if we are careful enough during our cut, during that cut, we will be removing a certain amount of material that is proportional to the width of the blade. And if we're not careful and we wobble all over the place, then we will remove even more material. And what does that mean? That means that once we're done with our cut, we take the cut pieces, we reshuffle them into a new shape, then the volume of the new shape will not be perfectly and exactly equal to the volume of the original. But evidently, what we're doing here is not the physical cutting, but what we're doing here is called mathematics. And according to one short enough and faithful enough definitions of mathematics, mathematics is a study of structure divorced from context, and that context itself is divorced from reality. In other words, mathematics is an activity which we do in a complete abstraction from reality. As such, in mathematics, a faithful model of a physical chunk of wood will be what? It will be called a cuboid, it will be called a rectangular prism, or a, for example, parallelepiped. And even though, yes, technically in this case, we remember that the Hilbert's third problem gives the answer to the problem of equi-decomposable polyhedrons in the negative. In this case, it is possible to do it, but what we can do here is we can take our piece of wood, which is a cuboid or a rectangular prism, and project it orthogonally onto a plane that is parallel to the face of our 8x3 chunk of wood. And what will we have then? In that case, we will have exactly a polygon, or we will have a rectangle. And at that point, we already know that the Wallace-Bolyai-Gerwien theorem is on our side. Why is that? Well, because the area of the projected cuboid, or the projected piece of wood, will be equal to what? The area of the polygon that is 8x3 in size, and that area will be what? 24 units of length. And in this problem, we're asked to cut the 8x3 piece of wood, or when we translate it into a new setting, we're asked to cut the 8x3 rectangle into two polygons, which, when recombined, will produce a shape that will cover a 2x12 hole perfectly. And that means that 2x12 is what? 2 times 12 is 24. So that is exactly 24. So a new shape will have exactly the same area. And by the Wallace-Bolyai-Gerwien theorem, we know that there is hope. If two polygons have the same area, then they are scissors congruent, or any one of these polygons can be cut into another in such a way that the finite number of pieces that were produced during the cut can be reshuffled into the body polygon. So that means that theoretically, that problem is not impossible. Whether we can come up or find the actual algorithmic solution is a totally different story, because mathematics is filled with situations where we know that the answer to a certain problem is in the positive, but we do not know how to construct that answer. For example, in real analysis, we learned that by now we have an impressive battery of the so-called convergent tests, and if we're given an infinite series, we'll look at it, we apply some convergence test to it, and we say, yes, this infinite series is convergent, it converges to a certain real number, but we have absolutely no idea what that real number is, what is the name of that real number to which this series converges. So here, at least when we step into the problem, we know that if we transform the pronounced 3-space problem in the 2-space problem, we know that according to the Wallace-Bolyai-Gerwien theorem, the theory is on our side, that there should be possible to do what we're asked to do in this problem. So if we apply the divide and conquer problem solving approach to the process of generating a solution for this problem, what should we do? The first step of this problem solving approach prescribes that we divide the monolithic whole into smaller and simpler primitive parts. What these smaller and simpler primitive parts should be in this case? Well, we answer that question by thinking about the numbers that were given, 8 and 3 and 2 and 12. What is 2 and what is 12? What is 8 and what is 3? Apparently, these are units of length. So this gives us an idea that a smaller and simpler or primitive part in this case could be basically a unit square. And with unit squares, what can we do? We can tile the entire rectangle, 8 squares lengthwise and 3 squares, let's say, height-wise, and we produce how many? We produce 24 unit squares. So far, so good. So we succeeded in carrying out the first step of the divide and conquer problem solving approach. We managed to partition or break up or divide the monolithic whole into primitive, simpler, and smaller and simpler primitive parts. Now, the next step in the divide and conquer problem solving approach prescribes that we try to find a solution for all the primitive parts. So in this case, what does it mean to solve a primitive part, or what does it mean to solve a square that makes up, the copies of which make up the whole in this case? Well, we all think differently. You guys can have a different bright idea. Don't be shy. Share this bright idea with us in the comments. My idea is the following: with each primitive part, with each unit square, what do we have? Well, we see that once these unit squares are tiled in a way that is shown over here, we generate a so-called finite unit square lattice. And this lattice consists of nodes. That's where the vertices of the square meet, and these unit squares tile the underlying plane tight with no gaps and no overlaps. Consequently, a solution of one primitive part can be exactly one step that we make in exactly one of exactly two mutually exclusive directions. For example, the direction east this way or north that way. And depending on how our squares are laid out, we may associate these steps with, let's say, one or two adjacent squares. But basically, now let's say we want to travel from the point A, shown over here, to the point B, shown over here. And if a solution of one primitive part is one step, either east or north, then the third step of the divide and conquer problem solving approach prescribes what? Find a way to combine all the solutions of all the primitive parts into a solution of the whole. So what does it mean to find a way to combine all the solutions of all the primitive parts into a solution of the whole in this case? Well, if we glue these steps either east or north continuously in such a way that we travel from the point A to the point B through a certain path, then that hopefully will produce precisely a solution of the whole problem, and that will precisely represent the process of finding a way to combine all the solutions of all the primitive parts into a solution of the whole. The resultant path in this case will be called a taxi cab path or a Manhattan path, because in many areas, for example, in Manhattan, the streets run horizontally from east to west and west to east, and the avenues run north to south, south to east, and in many places they intersect at right angles and they create actually a representative rectangular lattice, not a square lattice, but a rectangular lattice in many places, but not everywhere. For example, Broadway in Midtown makes a turn. But anyway, the point is this. If we combine each and every solution of a primitive part or a step, either east or north, into a path that leads us from the point A to the point B, for example, then we will create actually a partition of our parent polygon into two smaller polygons, a finite number of polygons, which we hope, when reshuffled, can create exactly the target shape that we're asked. And what does this remind us of? Well, this is exactly a chapter from the playbook called the Wallace-Bolyai-Gerwien Theorem. In other words, we model the process of combine the solutions of all the intermediate smaller parts into a solution of a whole with a taxicab path on the finite unit square lattice over here. Let's do one, for example. Let's say from the point A, we step this way. We go east, we go north, we go east, east, we go north, we go east again, then we go north, and we go how many times? 1, 2, 3, 4, we go east. This is our path. That is a model of the process called find a way to combine the solutions of all the smaller and simpler primitive parts into the solution of the whole. And here the question is, how do we extract actionable mathematics from it? Well, we already studied the so-called transform and conquer problem solving approach and reduce and conquer problem solving approach. So when we combine those, we transform this awkward angular path into a smooth combinatorial structure, which is what? Think about it on your own, put this video on pause, come back when you generate an idea, compare your idea to our idea. But our idea is the following. To each step, or remember, a solution of a primitive part, we correlate one letter. If the step is made east, we correlate with that step one letter. And if that step is taken north, let's say this way, north, then we correlate this step with the letter N. Then our solution of the whole, or the entire taxicab or Manhattan path, can be rendered which way? Well, it can be rendered as a string of symbols. For example, let us record our path or taxicab path that is shown on the board with this combinatorial structure. Well, what will we have? We will have one step east, one step north, another step east again, east, north, then east again, then north, and then 1, 2, 3, 4. 1, 2, 3, 4 steps east. And in combinatorial analysis, what is this called? In combinatorial analysis, this is called a linear permutation of a finite number of distinct items, each of which is available in a finite supply. That means that in our string or in our linear permutations, how many distinct symbols do we have? Well, in this case, because we can only step east or we can only step north, we'll have only two distinct symbols, either the symbol E or the symbol N. And what is the maximal number of symbols E that we can have? Well, the most number, or at most, we can have 8 symbols E. 1, 2, 3, 4, 5, 6, 7, 8. And by the way these things work, because we are looking for a shortest path over the unit square lattice from A to B. That means that we are not allowed to backtrack. If we made one step east, for example, over here, we cannot, in the consequent travels, step west. These are the only cardinal directions that are allowed. And if we step north, we cannot step south at any point. As such, we have exactly 8 letters E and exactly 3 letters N. So in combinatorial analysis, how many such linear permutations of a finite number of distinct items, each of which is available in a finite supply, are possible? Well, the way we construct this formula for the number of such linear permutations is a maneuver that is traditional in combinatorial analysis. We make each not unique item, for example, unique. We number those letters E1, E2, E3, and so on, all these numbers. And what is the total number of unique or distinct linear permutations of, in this case, P, 1, 2, 3, 4. We model the length with the number P and Q different items. Well, that number is given by, we know that P plus Q factorial. But we know that simply because we made all the elements in this linear permutation unique does not mean that this is how we leave things off. Now we need to remove this uniqueness. And how do we do that? Well, again, we use exactly the same idea. How many duplicate elements E will we have? Well, we'll have P factorial distinct ways to permute these distinct elements, and once we remove this distinction, we have to divide the total by the number of such linear permutations. And the same goes for Q, or 3 letters N. Once we remove their distinction, then how many duplicates we will have? Q factorial. So we divide this by Q factorial. And in this case, what does it mean? It means that we have 8 plus 3 factorial divided by 8 factorial times 3 factorial. This is how many distinct shortest taxicab paths we can take from the point A to the point B. And once we find such a path, what do? Well, we take our scissors and we cut along that path. You see, we cut along that path. And what do? Once we cut along the path, our parent rectangle, what do we produce? A finite number of smaller polygons, 2 pieces, which hopefully can be recombined in such a way that they will cover a 12 by 2 hole as demanded in the problem statement. Let us estimate, well, actually we can compute exactly what that number is. So this will be what? 11 factorial by 8 factorial times 3 factorial. 8 plus 3 is 11. 11 factorial. 11 factorial and 8 factorial cancel each other out to which point? We'll have 9 times 10 times 11 over 2 times 3. This is the leftover from the 11 factorial once 8 factorial is taken out of it. And then what do we have? 2 and 10 produce 5 in the numerator. 3 and 9 produce 3 in the numerator again. 3 and 5, 15. 15 times 11 is what? 165. So now we have 165 distinct paths from the point A to the point B over 8 by 3 finite unit square lattice. And the thought over here is the following. We can eliminate a fair amount of such paths, and if we play enough with these paths, we may eventually hone in on a winning path, so to speak. And that path will be what? Let me use, for example, blue chalk to record such a path. So here we will go one step north. We'll go north. So the winning path here is this, and north. Then we go east 1, east 2, east 3, and east 4 up to this point over here. Then we will do what? We will, so how many? North, 1, 2, 3, 4. 1, 2, 3, 4 steps east. Then we'll make one step north over here and again. So it will be north. And then what? And then 1, 2, 3, 4 steps. 1, 2, 3, 4 steps east, and voila, we'll close our path like so. It will be let's see which way, this way. Technically, if we want to get here, this will be another 1, 2, 3 step north. This is how we arrive at the point B, but that particular path produces what? A finite number of smaller polygons, which is what? This guy. Let me cross hatch it this way. And what will be the other one? The other one will run this way. This will be, so this way, you see, this way. These are the two. When we make our cut, unbuckle these two pieces, shift them one with respect to each other, and join them together. I'll show later in the episode a complete solution, but it is possible once we start playing with these paths onto which we hone through a combinatorial reasoning, that then eventually we will hone in on the winning taxicab path shown over here, and thus we solve the problem. Again, all courtesy of the divide and conquer problem solving approach. But let us assume for a moment that this combinatorial reasoning has escaped us completely. Is there any other way in which we can solve this problem? For demonstration purposes, let us assume that the bright idea of combining a little bit of combinatorial analysis with a little bit of geometry did not visit us. Things happen all day long like that, and can we still solve this problem in a different way? Well, still operating in terms of the divide and conquer problem solving approach, we already know that if we partition our monolithic whole with unit squares, then each and every such unit square will represent a smaller and simpler or primitive part. Very well, but in this case, what does find a solution for each and every primitive part can be interpreted as? Again, here in this case, because we are asked to produce two pieces that cover the 2 by 12 opening in the plane, that requirement is pretty tight. We want to somehow minimize the number of pieces into which we cut our parent shape. But as a first cut, as a straightforward solution, let us say that a solution of a primitive part means that we cut some of the primitive parts away from the whole and we leave the other parts intact. So this is our 8 by 3. Let's say it ends over here. I'll delineate right here. Ends right here. And what is the most straightforward way that does not require much intellectual voltage, so to speak? Well, we can cut away the top, let's say, 8 by 1 strip of our rectangle, and we produce 8 distinct or cut, parted from each other, 8 squares. And once we have these 8 squares, we can pour all these 8 squares. This will be the third and the final step of the divide and conquer problem solving approach. Find a way to combine all the solutions of all the primitive parts into a solution of the whole. So what does this step look like in this case? In this case, this step looks like as follows. We grab all our 8 primitive parts and we pour them onto the plane in such a way that we tile that plane again with 4 by 2 polygon, the smaller polygon, in such a way that the final shape will be what? 8 and 4, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 primitive parts wide, and how many? 2 primitive parts tall. And this is what? 12 by 2 rectangle exactly covers the 12 by 2 opening in the plane as demanded, except that our solution cost us how many steps or how many primitive parts? Well, let's count. We have 1, 2, 3, 4, 5, 6, 7, 8 squares on the top, which were completely cut away from the parent polygon, and we have one piece that is 8 by 2 at this point long also. So this makes it what? 8 plus 1. This is a 9. This is a 9 piece solution, and we're asked to produce a 2-piece solution. So what does that mean? It means that this solution is no good, but the way things work in mathematics, we now step back and we pose the following question. Can we optimize the number of the parts into which we cut the parent polygon even further and make that number smaller? Again, we're all wired differently, and it's a very good thing that we think differently. And as such, in real time, when we work on a problem in mathematics, for example, we may step in different directions, we generate different ideas, we try and fail many times, and luckily we fail more often than we succeed, because if we were succeeding all the time, then how much fun would it be to do mathematics? The fact that in mathematics pretty much everything is difficult and barely possible is what exactly makes mathematics fun. So here, once we step back and look at our 9-piece solution, here still operating under the umbrella of the divide and conquer problem solving approach, again, we go back, primitive parts, break the monolithic whole in the primitive parts, solve each and every primitive part. But here, during the second step of the divide and conquer problem solving approach, we decide to do what? Instead of cutting every square in the top 8x1 strip of our parent rectangle, what do? Well, we double up the amount of squares that we keep in every cut. So we cut at every second. We cut at every second square, and then what do we have? We have, let's see, 1, 2, 3, 4 dominoes, and in the previous 9-piece solution, what did we do? When we poured all these 8 unit squares to the right, let's say, of our rectangle to form a 12x2 rectangle, we put them in any which way but one by one, and that was pretty much it. In this case, when we have 4 dominoes, how can we arrange them or stack them up into an 8x2 rectangle? Well, we can stack them up lengthwise, for example, this way, this way, this way, and this way. Or we can stop them this way. We stack them up, let's say, horizontally, and this way, but the other way we can stack them vertically. For example, we can put them this way, 1, 1, 2, 3, and 4, and thus we arrange an 8x2 rectangle. But let us count the cost of this solution. We still have 1 8x2 residue, so to speak, of the parent polygon, and then on top, how many pieces do we have? 1, 2, 3, 4. 4 plus 1, 5. This is a 5-piece. This is a 5-piece solution, and we now still think, can we optimize or can we reduce that number any further? Cutting to the chase, in our next optimization, we step back from our 9-piece and 5-piece solution and think, why don't we cut the top 1x8 strip in our parent polygon, not in 1 and not in 2, but in quads? So in other words, the top 1x8 strip of our parent polygon we cut exactly in half. This way we have sort of 2 dominoes glued together. We have 1 quad and another quad, and this will produce what? 1, 2, and 3 8x2 rectangle. This will produce a 3-piece solution. Exactly, this will be a 3-piece solution. 3-piece solution. 3 is still larger than 2. We're asked to produce 2, but in this case, if we try to generate, this was again, we go back to our first step of the divide and conquer problem solving approach, break or divide the monolithic whole into primitive parts. These are our unit squares. This time generate the solution for each part. Keep the 8x2 conglomerate of primitive parts together. Cut the top strip of this primitive parts in half. Produce two quads. But then how do we find a way to combine all the solutions of all the primitive parts into a solution of the whole? In this case, we have, it looks like, the least amount of freedom, because these 2 quads cannot be stacked vertically, because then they will not produce the 12x2 rectangle that is sought after. But here we have pretty much only one possible solution, only one way to combine all the solutions of all the primitive parts into a solution of the whole. We can only arrange these 2 quads horizontally. We put one, let's say this quad we put on the bottom, and on top of that quad we put the second quad. Bam. we arrange these two quads horizontally, so to speak, and voila, we have our 2 by 12 rectangle that exactly is sought after, except that this solution is a 3-piece solution, not a 2-piece solution. But again, the way these things work in mathematics, once we play around with these solutions, once we play with these primitive parts, then the chances are that we will hone in on the idea that what is going on here with these quad pieces. Well, the quad pieces are exactly what? 1/2 of the length of the parent 8 by 3 rectangle, and that means precisely that if we cut our parent shape in such a way where we keep only one quad on one side and one quad on the other, parabolically speaking, for example, 1, 2, 3, 4, this piece right here, this portion right here, this portion right here exactly represents one such quad. Then we step up and then we cut this way, and voila, we produce a solution. And now we have just one more mechanism through which we can find a solution of this problem to look at, and that mechanism is known as symmetry. Symmetry plays a very important role in both mathematics and theoretical physics. In mathematics, for example, the entire study of the theory of groups is the investigation of what symmetry means in mathematics. And in theoretical physics, there is a very famous theorem due to Emmy Noether, which says that if a system, if a physical system possesses a certain symmetry, then continuous symmetry, then this continuous symmetry corresponds to a conservation of a certain physical quantity. And for example, if a system possesses a symmetry under time translation, then in that system the energy will be conserved over time. And if a physical system is symmetric under spatial translation, then that means that that system possesses the conservation of momentum over time. And that means that anytime we look at any mathematical problem, for that matter, we should try to see or try to investigate if we can somehow capitalize on the underlying symmetry in the problem. And sometimes that symmetry lies on the surface, sometimes we have to dig deeper, but sometimes it's quite helpful. In this case, if we, for example, were not able to generate the idea of the combinatorial argument, or we could not generate the idea of, for example, slicing off the top 1 by 8 strip in our 8 by 3 rectangle and then cutting it up into pieces and making these pieces larger and larger and larger, then we may actually have an idea or just generate a thought that maybe our solution is symmetrical. Then how can we generate it? Well, in a rectangle, what we can do, we can, for example, connect two diametrically opposite vertices of such a rectangle with the diagonals, and the diagonals in any rectangle intersect where? Precisely, they intersect at the point called the center of a rectangle, and every rectangle is a figure that is centrally symmetric. And what does that mean? That means that any straight line that passes through the center, any straight line that passes through the center of a rectangle will intersect the opposite sides of this rectangle. Let me maybe mark it in green. This point and this point, and these 2 points, point let's say P1 and point P2, will obey the following or honor the following 2 constraints. These points will be equidistant from the center, and both of these points will belong precisely to the boundary or the periphery of the rectangle. So now that we locate the center of the rectangle, that is 8 by 3, the given rectangle, then we may get the following bright idea. If our smaller rectangles, smaller polygons into which we will eventually cut our parent polygon is asymmetrical, then what if from the center of this rectangle we make one step north in as much as we make it the same step south. And we obtain this cut over here along the center line shown over here in red. Let me try to make it a little thicker so you guys can see it. But anyway, the idea is again to exercise or capitalize on the symmetry of the underlying shape of the 8x3 rectangle. We locate its center. From the center, we step north by exactly the same distance in which we step south this way. And then again, we develop or maintain that symmetry by either way. You can go, for example, west first, and then you will balance each step west with a step east, or the first step over here could be, let's say over here could be east this way into here. And in order to maintain the symmetry in this arrangement, what do? We make one step west this way so far. And we maintain that symmetry as we develop our solution step by step. If we make one step east again, this way, one step east along the primitive part, then we make one step west along a primitive part, corresponding primitive part over here. And then we keep doing it little by little, step by step. We make one step east and we balance it with one step west, one step east, and we balance it with one step west. And by the time we come, again, if we were to, for example, bring in the combinatorial argument that we saw we generated earlier, we'll come over here into this diagonal, here we'll come into this diagonal, but at this point, these cuts can be sort of null cuts, if you will, or identity cuts. Here we don't really have to cut anything. We take our 8x3 rectangle, we cut it along the bottom 4 quads, then we make one vertical cut, and then we cut 8 more quads, and voila, we have our solution that is exactly 2 pieces. It will be this piece right here, the one, let's say, that sits over here. I'll cross hatch it in red, and the other piece will be what? The other piece will be this guy. I'll cross hatch it in green. You see, it will run this way, and indeed these 2 pieces are symmetrical. Once we execute these 3 cuts, we shift these 2 polygons, smaller polygons, with respect to each other. We'll, let's say, shift this polygon east, we shift this one west by exactly 2 units, let's say 2 squares, and then we jam these 2 guys together. And what do we form? Precisely, we form 1 12. We form exactly 12 by 8 rectangle. And if we do that, what will we have? Well, this polygon will be shifted over here into this position right here. This polygon will be shifted over here, and it will run this way, this way, this way, and this way. This will be this polygon. See, this guy. And then this polygon over here will run which way? Well, we'll simply jam it down. So this polygon will come down over here, and it will become this guy. This, and this. And voila, we have our 2 by 12 hole that is covered with exactly 2 pieces, and the problem is solved. In Season 1, Episode 2, where we explained a way to practice mathematics correctly, we mentioned the fact that after we solve this or that problem in mathematics, theoretical physics, or computer science, we should step back and reflect on our problem-solving experience. Here, let us do that together and reflect on exactly how did we apply the divide and conquer problem-solving approach to the process of generating a solution of the mathematical problem S2E37. Well, in this case, we followed exactly in the footsteps of the divide and conquer problem-solving approach, where we did the divide, we did the solve, we did the combine. In other words, in the first step, we divided the parent monolithic whole which was an 8 by 3 rectangle, into the primitive parts or unit squares. And that was one and the same step pretty much in all three different ways in which we solved this problem. In the second step, where we generated a solution for each primitive part, what did we do? With the combinatorial argument, we suggested that we associate one step, either north or east, with each primitive part. In the second solution, where we cut off the top 1 by 8 strip from our rectangle, the solution was to cut that many squares from that strip. And in the third way in which we solved the problem, what was the solution of a primitive part? Well, again, it was a step. It was one step. We did not really call it in dedicated manner the way we did it in combinatorial analysis, but we introduced the idea of symmetry, and that naturally led to what? Step east, step west. And that step, that single step, was a solution of a primitive part. And in the final step, when we found a way to combine all the solutions of all the primitive parts into a solution of a whole, what did we do? In the first case, when we generated a happy combinatorial idea, we glued all these steps together into a taxicab path over the unit square lattice that was generated by the primitive parts that tile the parent monolithic whole. In the second case, we basically took our pieces that we cut from the top strip and we poured them in to the polygonal area over here shown in the right in different ways, one square at a time, domino at a time, or quads at a time. And in the third case, when we solved this problem using the idea of symmetry, we simply maintained the symmetry on every step by connecting the final point of the previous step with the initial point of the next step. And this is how exactly we apply the divide and conquer problem solving approach to the process of generating a solution of the mathematical problem S2E37. Now that we're done with that solution, we will move on to a new challenge next. Our next challenge will be mathematical problem S2M40, and in that problem we're given a regular hexagon with a side length of A. Here I depicted such a sample regular hexagon in white, 1, 2, 3, 4, 5, 6, with the side length of A, and A. And we're told that every other vertex of that regular hexagon, for example, for demonstration purposes, let us this vertex be this one, skip this one, skip this one, and we skip this one, we come back to the original one. And we're told that every such other vertex plays the role of the center of a circle whose length of the radius is equal to the length of the shortest diagonal seen from that vertex. For example, in this case, the length of the radius of the corresponding circle will be equal to the length of this diagonal right here, because this diagonal that connects the opposite vertex of the regular hexagon generates a length of a diagonal that is larger than the length of this diagonal. Evidently, due to the symmetry of the underlying shape, the distance from here to this point is the same as the distance from here to this point. As such, we stick the needle of the compass into this point, we open it up to this distance or to this distance, and we transcribe the circle entirely that way. In theory, we can draw the entire circle, but obviously for illustrative purposes, I only drew the portion of that circle shown over here, this part. And then we repeat the same exactly experiment in the remaining two vertices, this one and this one. Here we put the needle of the compass into this point, open up the compass to this distance from here to here, or from here to here, and we transcribe the circle that goes this way all the way around. But again, here I only show a partial circle arc, this one, and we repeat the same experiment in this vertex. We stick the needle of the compass over here, we open up the compass to this distance or this distance. This distance is longer, we throw it out, so this distance or this distance, and we transcribe the circle in the plane exactly like that. It's supposed to be complete. circle, but only a partial circle shown over here is enough. And here is the challenge in this problem is to find the area of the place where all three circles in the plane intersect. So in other words, we're asked to find the area of the planar region that is the result of the intersection of all these three circles, three distinct circles, but the circles that have one and the same length for their radius. I cross-hatched that area in red. You should see on your monitors in a good way. So the question is, what is the area of the colored in red region that looks like a triangle whose sides are circular arcs? This arc, this arc, and this arc, and we're seeking an answer as a function, this area of this funky looking triangle as a function of the length side A of the parent regular hexagon. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode in which I will share my solution of the mathematical problem S2M40.